All right. Looks like we're good with our settings. Everything looks all right. Okay, hello. Welcome on in. Going to discuss some stuff. Looks like you have some homework due before the next time we meet. And then shortly thereafter, you have the project part of your binomial distribution. So I added this in here, I don't know, a couple days ago. But keep in mind, you've got... there was a survey question, or at least my recommendation to you was to make a survey question that had a two-part outcome: yes, no, true, false, agree, disagree, something like that, where there's just two outcomes, right? And it was for this right here, so that you can do this stuff we're learning in this chapter. You can do this part for your project. So if you have that, then feel free to use that problem for trying to use things from this chapter in order to do your binomial distribution stuff. Just take things from this chapter and apply it to that question. Just show me that you learned something from the chapter. Some people did not follow my advice, and some people did not pick the kind of questions that I recommended you pick. You can just go to the survey. Remember, you can pick someone else's questions and use those as well, right? You're not confined to use the questions that you developed or that you created. You can use the other ones as well. So even if you didn't create a binomial type question that is a two-question outcome, a yes, no, true, false, agree, disagree, something like that, just go in the survey and grab someone else's and use that to do your work, okay? And then, so just be aware, November 7th. So we'll see each other before that. I think we don't have any holidays or anything next week. So just be on top of that so you can take care of this and get your points, right? These early points right here are easy points to put towards the project. The grading on your final project is harder than the grading in these earlier parts. So you really want to make sure you get all these point opportunities early on, because it helps kind of even out the grade for your project. If you don't get those points early on, well, then of course you get 0 on those assignments, which is going to drag your project down. But also that means the only grade that you do have in the project is where the grading gets a little bit harsher, right? So you definitely want to make sure you're not missing these along the way, okay? So let's get into it. Let's talk about, we talked a little bit last time about variables, and we learned some new terms and ideas for variables, and, discrete versus continuous. Remember, discrete is where you can break things into specific chunks. Something like an eye color. If I ask you what is your eye color, and there's blue, green, brown, pink. Let's see, what else could be blue, whatever the colors are that people can have. You're in one of those boxes, right? You're not like, well, I'm half blue, half green. I guess some people can. I forget what that's called. But assuming that you don't have like the two different color eyes or some kind of very rare eye condition. Some people have like the part of their eye with the color actually can have a little hole in it, like in the color part, and you can see through to the other part. Assuming none of that, you just fall in one of those boxes. Oh, I have green eyes, I have blue eyes, I have brown eyes. There's not like a continuity there. There's no logical ordering of those things. Whereas, say, temperature it has an infinite number of temperatures you can have. Now you may go, well, isn't it still just integers, so you're breaking it into boxes? You can measure temperature as being 79.8345 degrees, right? We don't usually do that. We usually just say it's 78 degrees or it's 79 degrees. But you can go in and you can track temperature as accurately as you want to do using the technology that you have, and it's on a continuum, which means, if you start with your temperatures from lowest to greatest, then you're moving along a continuum till you get to the end. Whereas that's not really the case with eye color. Eye color, you don't as you move through the blue box, you don't end up in the brown box, right? You're either in the blue box or you're in the brown box. But with temperatures, you can break those up in different ways, whereas you move through 71.1, 71.2, then you up in 72. Right, so you see, you can always break it down. Think of it this way: between any two temperatures, is it possible to have another temperature in between? Yeah, right. Take 71.1 degrees and 71.2 degrees. Yeah, you could have a temperature in between those. You have 71.15 degrees, right? And you can keep finding legitimate values in between any two that you pick. then you're on a continuum. That's kind of a math idea, sort of carried over into statistics, but that can help you determine the difference between a continuous and a discrete. For discrete, can you put things in convenient little boxes, okay? And then we're going to get into some new ideas today. We're going to look at a couple of examples, kind of fun examples like you're going to learn today. You can literally make your own dice games, right? And then you can figure out if it's to your benefit or someone else's benefit, or is it a perfectly fair game? Who knows? You can actually sit down and calculate that kind of stuff. So we'll take a look at that when we do expected value. We'll get back to that in a minute. Let's see, I already talked about that. Where am I? Lost my place here. Oh, right. So I need to go back up to here. So we talked about some of this. I think we left off with expected value, I believe. There we go. We were just about to learn what expected value is. We kind of left off looking at these formulas last time. And this looks like this right here. What the mean for a probability distribution. How does that work? Is if you think about it, it's kind of a complicated calculation to make. If you don't have a big list of data, you just have outcomes and probabilities of that data occurring. It can be tricky to try to figure out what the mean would be, especially if you're in a situation where the probabilities are not even with each other. Like we're gonna create a dice game here in a little bit, and we can figure out, is this one where we expect that me, the person running the game, would end up winning? Right? That's how casinos do it. Every single game in the casino is optimized so that the casino has a very slight advantage. That way, over time, if you keep playing long enough, the law of large numbers says those true probabilities are going to come out. Eventually, the casino is going to get your money. Right? Right. So, but this can be hard to calculate. Do you have the advantage? Does the player have the advantage? Is it even? Right? What is it we're doing here? And there's some other stuff in here. If you have questions about that, feel free to come ask me. But we don't mess around too much with that stuff. A little bit, but not too much. So the important thing for today is understanding what is expected value. What is the expected value of something? And expected value looks complicated, right? Here we're seeing this thing again. Maybe I can make this a little, that should be a little bigger. Sigma x times p of x. This, a lot of times for people in mathematics and statistics, half the confusion comes from notation. So a lot of times just understanding the notation, and you realize, like, because right now I don't know, it looks like some, aliens came down from space and handed us some kind of symbols from their language. I don't know what any of that means. But in this case, it's actually a fairly simple formula. If an individual can just sit down, and sometimes it takes just 5 minutes, sit down and force yourself to understand this formula, you go, oh, that's all that's going on? That's actually a much easier concept than I thought, but it's easy to get really hung up on the notation because notation can be tricky, right? And here we're seeing it up here for the mean of a probability distribution. It's sigma times x times p of x. What does that mean? Remember, sigma means you're going to add up all the stuff. X is the outcome that you're looking at, and p of x is the probability of that outcome occurring. So for each possible outcome, you take the probability of that thing occurring times the outcome, and if you add all those up, you get yourself the mean, right? You get the mean of that thing. So let's read the official definition. And just know, you can apply expected value to all sorts of stuff. You can apply expected value to the lottery. Like, I do this occasionally myself. You're at the gas station, Powerball's particularly high, you buy a Powerball ticket or a Mega Millions or something like that. I realize from a mathematical standpoint, I'm throwing my money away, but if I can buy a little fantasy for a few minutes for $2 that I'm going to, be worth hundreds of millions of dollars, is sort of a cheap entertainment, right? But you can apply expected value to, say, the lottery. Now, it doesn't work very well because generally there's like one winner and millions of losers. So your expected value is not as useful in that case. But you can calculate it, and you can go, oh, okay, I see that it's a losing proposition for me. I'm throwing away money each time I do this. But you can apply it. You can apply expected value to a lot of casino games. You can apply expected value to games you make up. You can apply expected value, like I do this sometimes in real life, where we're making a decision at work, or I'm deciding, which type of insurance can I get? There's so many insurances now available to people. You can overwhelm yourself. You've got life insurance, you've got earthquake insurance, flood insurance, and you can sit there and you can kind of think, okay, what's the probability of this kind of event occurring? What's the payoff going to be in that kind of situation? Which is the one I want to go with? Because the reality is most people don't have all the insurances because it costs a lot. So you can use this in financial decisions that you're making, right? Situations. Expected value is a hugely useful tool. Definitely, I think it's one of those tools that, it's one of those things where people are like, well, when am I ever going to use this? And it's like, you'll get through life without using it. If you never use expected value again in your life, like, you're not going to die from it probably, but you will miss out on making the right decision sometimes. You'll miss out on making the informed strategic decision and just kind of go with whatever the salesman's trying to sell you. So expected value can be hugely helpful in making decisions, and I do it from time to time. The expected value of The expected value of a discrete random variable x is denoted by E. So E just means expected value, nothing fancy yet, and is the mean of the value of the outcomes. So E equals mu. So that's why, remember up here, we're seeing this formula, mu equals the sum of the outcomes times the probabilities. And notice that's the same one down here. It's the sum of the outcomes times the probabilities of that outcome. So E can also be found by evaluating sigma of x times P of x, as in formula 5.1. So that's where it comes from. It's really the mean of a probability distribution, but we call this expected value because expected value is when we start applying it to things and like learning things and go, oh, I shouldn't play this game because I'm expected to lose. Every time I play, on average, I'm going to lose a quarter. Okay, well, then I shouldn't play long term, right? You might play, like we talked about that earlier, you might play short term in a casino game and get ahead, but if you play long enough, you're going to end up on the losing side, right? An expected value need not be the whole number. In fact, it generally, a lot of times it won't be. Even if the different possible values of x might be whole numbers, we're probably going to see that when we make our own little game here in a little bit and apply expected value to it, is that on any given round, you're either going to win $1 or pay $2 or, whatever we decide our game should be. But your expected value can still be a fractional value. We say the expected number of girls in 5 live births is 2.5, right? You expect about half and half, but you can't really have 2.5 girls when you have 5 children, right? Even though 5 specific births can never result in 2.5 girls, if we were to survey many couples with 5 children, we expect that the mean would be 2.5, right? So you're going to get a lot of people that have 3 girls and 2 boys, a lot of people that have 3 boys and 2 girls. But on average, you would expect that mean to be right around 2.5, even though for any individual family, it's impossible to have 2.5 girls. So the expected value is one of these ideas that we think about over a number of trials, right? We're not thinking, oh, this is what I'm going to win if I play once. No, in any given instance of a round of something involving expected value, you could get any of the outcomes. But in the long run, your wins and losses will be dictated by the expected value, right? It's sort of following the law of large numbers. Okay, so then they kind of break it down in the book. What does this mean? The sum of x times P of x. So let's look at this problem. Oh, right. So we're back to that number of girls in, was it 5? Number of girls in 2 births. Okay, so you're going to have 2 children. What's the probability that you end up with, what is the expected value for the number of girls? So they want us to find the mean, the variance, and the standard deviation. So I'm going to show you the mean because we're really talking about expected value right now, but you can see there's the other formulas for variance and standard deviation as well. So what I'm trying to do right now is get you to understand what this sigma times x times sigma of x times px means. What does that equal to, right? What is the outcome? So our x's are the outcome, which is, well, if you're going to have 2 children, there's 3 outcomes for the number of girls that you can have. You can have 0 girls, which would mean that you had 2 boys. You can have 1 girl, which would mean you had 1 boy. You can have 2 girls, which means you had 0 boys. Okay? Now, let's look at the probabilities associated to that. We get 1/4, 1/2, 1/4. Now, why is that again? Do we remember why that is? If you write out the probability space here, it's not just these 3 outcomes. There's actually 4 outcomes for having the children. There's that you have boy, boy, right? You can have a girl, then a boy. You can have a boy, then a girl. Or you can have a girl, then a girl. So there's actually 4 outcomes, and 2 of them result in having 1 girl and 1 boy. So that's why this probability is 0.5 in the middle, because it's 2 of the 4 possible outcomes. That's why it's 0.5. So if you're not understanding where these probabilities come from, ask. We talked about it last time, but I can go over it again. But it's 1/4, 1/2, 1/4, because there's actually 2 ways that this middle one can occur. Okay, so see what they're doing here? They're taking the outcome times the probability. So you're taking here's our outcomes, here's our probabilities. It's the x times px that's in this formula. X times px is this column. So what do? You take 0 times the outcome times the probability is 0. 0 times 0.25 is 0. 1 times 0.5 is 0.5. 2 times 0.25 is 0.5. So when I add up these probabilities, I get 1. That's the sigma part. That's where we add things up. So it's saying take every single possible outcome times its probability and then add all those up, which we do coming down. And what do you get? 1. So it meets our intuitive definition of, well, if you're going to have 2 kids, what's the expected value for 1 girl and 1 boy? And most people can tell you, oh, it's 1. But then when you try to, like, okay, how did you calculate that? I don't know. It just seems right. It's just intuitively, I feel like it should be 1, which is good, but that's not really like knowing what you're doing, right? So it's important that when you get to the more complicated problems, you understand this process of taking the outcome times the probability, and then when you add those up, that gives you the mean, what they're calling the mean of the probability distribution. It's the expected value. So if you're going to have 2 kids, the expected value is that 1's a girl, right? Some people will have 2 girls, some people have 0. The expected value is that you have 1. And then, you know, your formula for variance and stuff, you just take these values again and use them over here, okay? Right, let's see, what did I want to say? Trying to find the next thing I wanted to talk about. Forget what page it was on. Okay, let's take a look at a game, and then we'll make a game, and we'll see how easy it is to apply expected value to stuff. So, gotta move this over. Okay. Okay, so here's the deal. Very simple game. You have $5 to place on a bet, and you want to walk into a Vegas casino. You got $5. You're going to bet it on one thing, and then you're going to go, okay, I got that out of my system, and you're going to leave before they get your whole life savings. You have $5 to place on a bet in the Gold Nugget Casino in Las Vegas. You have narrowed your choices to one of 2 bets. You can walk to the roulette table and bet on the number 7, right? You like number 7. It's snazzy to you. So you're going to either go bet on the number 7 in roulette, or you're going to walk over to the craps table and bet on the pass line in the dice game of craps. Now, some of you probably don't know what the pass line is. Most people don't actually know how to play craps. Usually it's one of the better games to play. If you're going to play in a casino, you can play a lot longer before they get all your money, as opposed to like blackjack and stuff like that. But how would we calculate? Basically, we're saying which is the best bet if you're going to go in there and make a bet. right? Number 7 on roulette or the pass line. So if you don't understand those games, that's perfectly fine. We're going to discuss them. So here's your 2 outcomes. If you bet $5 on the number 7 in roulette, the probability of losing $5 is 37 out of 38. There's 38 numbers on a roulette table. There's a number of different ways you can bet on roulette. You can bet black or red, and most of the numbers are black or red. Usually there's at least one green. That gives the casino their little bit of edge, because that way when the green, every once in a while, a few times an hour, when the green one pops up, then anyone who's bet on red or green loses. Both sides lose. That's where the casino gets their little bit of edge, is by taking that bit away. And also that there's this part that comes out. So 38 numbers on the board. So when you win, they give you. Let's see. I'm trying to remember. They give you. It's 38 times. You bet you. Let's see. Yeah, I think they give you 38 times what you bet, if I remember correctly. Let me double check that math. Let's see. So we're looking at 5 times 38. It's 190. Oh, let's see. So I guess, do they give you 37 times? 185. So they give you like slightly less than 38 times your amount. So basically you're going to win $180. That's, again, they don't give you quite back what a true fair game would give you. In a true fair game, it would be 38 times 5. You'd get $190 back, including your original bet. So the prize, the net gain, is $175. So we don't need to break down the whole game of roulette completely. Just know that you're going to bet $5 on the number 7. The probability of losing $5 is 37 out of 38, right? Because there's 38 possibilities. 37 of them are losing numbers. 7 is the only winning number. So you have a 1 in 38 chance of winning. You have a 37 and 38 chance of losing. But when you lose, you just lose your $5. When you win a bunch more than your $5. Not quite as much as would make this a fair game, but your benefit, your gain, is $175. Okay? So what you would do then is you're going to take let me jump over to Wolfram Alpha here. You're going to take $5 times actually, this would be negative $5. This is Wolfram Alpha. It's a computation engine. It can be very helpful. Google is a search engine. There's all sorts of information in the world, and Google has categorized it, and they've done all their magic so they can find all the information. So when you put something in Google, it can quickly, all it really does is direct you to the information, right? Google doesn't actually answer any information from you. It just says, oh, you're looking for, whatever, hypoallergenic dog food. Okay, here's some sites that talk about hypoallergenic dog food, or whatever it is that you're looking for, right? Wolfram Alpha is they call themselves a computation engine. That is, they can compute a lot of things. So they don't find where the information is. They are an engine that does calculations for you. So you basically think of it as a super fancy calculator, right? So negative 5 times so negative 5 is our x. That's our outcome. Times 37/38. And I hit enter, and it comes back with negative 5 times 37/38, and it gives us our decimal approximation for that value. Right, so that's this right here. There's our x times p of x that we just calculated right here, 4.868. We've got that right here for our x p of x. So that's the first outcome. That's our x times p of x. And then what about when we win? Well, so I won't go because they've done the calculation right here. So I won't do it in Wolfram Alpha, and we're kind of losing time quickly. We may not have time to get to everything I was hoping to show you today. 175 times 1/38. So that's your other probability. There's two outcomes. You win or you lose, right? Here, you lose $5. That's going to happen almost all the time. You end up losing 4.86 each time you lose, $4.86 each time you lose. When you win, or that's the expected value, right? I just said that incorrectly, but this is, just think of this as the outcome times the probability. Over here, our outcome is that we win $175, but that's only going to happen 1/38th of the time. In that case, we get a positive 4.605. So when we do the sum of those, remember your capital sigma, your sum, when we add those, we get a rounded value of negative 0.26. In other words, if you keep playing roulette all day long, like you just sit down and you're like, I have tons of money, I'm going to put money on number 7 all day long, on average, you're losing a little over a quarter every time you play, right? Now think about that. There's never a round where you lose 26 cents because you can't bet 26 cents. So there's never a round where you lose 26%, but that is your average. That is the expected value when you play roulette in this way. You're expected to win expected to lose about 26 cents every time you play. Okay. Then we go to crap. So what have they done? They've got the outcomes for the pass line. Either you win $5 or you lose $5. They've got the probabilities for that, and then you just multiply across. You get your outcomes. When you add those up, right, that's the sigma part, add these up, you get negative 0.07. In other words, each time you play at craps, you're expecting to lose about 7 cents. Okay, you're never going to lose 7 cents in one round. Remember, that's not possible, but this is the mean. This is the mean that we're talking about when you play all afternoon, right? You play hundreds and hundreds and hundreds of these hands. The expected value is that you're going to lose about 7 cents per round. So if you're just trying to see how long you can make things last, maybe you go with the 7 cents. Now, it usually takes them a little longer to do roulette. I think the craps table moves a little faster, so you may end up as far as time, you may end up losing about the same amount of money over time, but you can see for each round you're doing worse with the roulette. Okay, so you'll have problems where you can break those down as well. Okay, not going to have time to do some of the stuff I wanted to do, like where we make our own game, although it's kind of an interesting thing to go through and do, but I need to get into the new material here so that you are all prepared, and it makes a little more sense when you watch the videos and the lessons and make sense of those. Okay, a binomial probability distribution results from a procedure that meets all of the following requirements. So this was kind of the title of the chapter, right? Or sort of, we're talking about binomial probability distribution. So let me help you make sense of these 4 things. All 4 of these have to be satisfied, or you do not have a binomial probability distribution, right? So step 1, the procedure has a fixed number of trials. A trial is a single observation. In other words, this is a key part of statistics that people sometimes ignore, and there was kind of a big controversy the way that statistics is being done in research areas that are not traditionally math areas, specifically psychology. There were a number of psychology journals that got in trouble about, 8 years ago, where the way the psychologists were running, and this is totally, they might not have even understood statistics well enough. So this is an example that there's many, many ways where people use statistics that don't really understand statistics that well, and they mess it up really, really bad. Or sometimes people are just, they know what they're going to get rewarded for, so they do this in order to get things to come out how they want, is they would keep running trials until they got numbers that supported what they were saying. That is totally unethical because it's completely throwing your statistical values out the window. You're basically cheating the system to end up supporting what you want if you're saying that, like, I'm going to keep repeating this until the numbers are good for me. You have to say, we're going to do this 500 times. We're going to do 1,000 times, and then you go do it. Okay, so the procedure has a fixed number of trials, right? So that's been fixed. This thing happens once, or it happens 10 times, or whatever, right? The trials must be independent. The outcome of any individual trial doesn't affect the probabilities in the other trials, right? So when we roll that marble on a roulette table, it doesn't matter that the last 10 outcomes came up black. It's still 1/2 probability of red on the next one. Okay, so they're independent events. Each trial must have all outcomes classified in 2 categories, commonly referred to as success and failure. So I had you ask a question like this with 2 outcomes, right? Just 2, or I suggested that you do, literally so that you could do this part of the course. That's why I had you ask that. Now, in statistics, they use the words success and failure, and those words in everyday English come with connotations. That is, there's like extra baggage when we use those words. In statistics, that baggage gets thrown out the window. When we call something a success, that doesn't mean it's a good thing. When we call something failure, it doesn't mean it's a bad thing. For instance, if you're studying cancer, depending on what you're studying, if you're counting cancers in the population, then you would call the cancer a success. Now, that sounds bizarre as a normal human being, that like, what? You think it's a success that someone has cancer? No, we're not saying it's a good thing. We're saying the thing we're looking for, we found and counted it. So that's the word success and failure. Like, don't bring over your normal definitions from everyday language that we use. It doesn't mean good and bad. It just, a success means you found the thing you're looking for. A failure means you didn't. So you look at someone, oh, you're cancer free. Sorry, you're a failure. Like, you're not saying that person is bad or that it's bad they don't have cancer. You're just saying, I can't count it as a result. And then you get to the, as far as a positive result. Then you get to the next person. They do have cancer. That's terrible for that person. You feel bad for them. You wish they didn't have cancer, but you found the thing you were looking for. So that's called a success. So don't get thrown off, because I see students sometimes get confused with that, because they're like, what? How can you say it's success if someone gets cancer? We're not using the English vocabulary definition of success and failure. We're using the statistical definition, which means success means you found the thing you're counting. Failure means you didn't. All right, so don't get hung up on that. And number 4, the probability of success remains the same in all trials. Right? So in other words, each time we do this, the probability remains the same. Okay, if all four of those things have to be satisfied, then you have a binomial probability distribution. Little bit of notation that you'll need to know for this. Basically, we have 2 outcomes, right? So we have 2 categories, a P and a Q. We're used to P being probability, but there's an opposite probability here, right? If there's 2 outcomes. So we could say, what is the probability that a person in our class has been to Disneyland? Okay, and then everyone in the class would respond if they've been to Disneyland or not. Now, I don't know what the probability is. I highly doubt that it's, 1/2 and 1/2. I don't know. I don't know what we would come up with. But let's just say there's a 65% chance that someone's been to Disneyland. So the probability would be 0.65. Then what is the probability that someone has not been to Disneyland? It would be 0.35. It would be the complement, whatever's left over. So if you have the probability of your success, whatever you're counting, the probability of the opposite, we call that Q. That's 1 minus P, because there's only 2 outcomes. So if you know someone hasn't been to Disneyland, like if they're not in the first category of people who went to Disneyland, then they're in the category of people who didn't go to Disneyland, right? So you're seeing getting your second probability is really easy to calculate. Once you get your first one, it's 1 minus that. Okay, so you see these P and Qs coming up. P denotes the probability of a success in one of the N trials. Q denotes the probability of failure in one of the N trials. So just Q is like another probability. That's all it means. P is the probability of the thing you're counting. Q is the probability of the thing you're not counting. Okay. Yeah, and your X, the number of successes has to match P, right? They're just saying that in this little box. So here's an easy one. We've got when an adult is randomly selected with replacement, there is a 0.85 probability that the person knows what Twitter is. So you just go up to some, and this is old. I suspect more people know what Twitter is now. This is an old edition of the book. But they're saying you just go up to some random adult. You say, hey, do you know what Twitter is? There's, 85% of the time they're going to go, yeah, I know what Twitter is. And 15% of the people are going to go, what? What are you talking about? So suppose that we want to find the probability that exactly 3 of 5 random adults knows what Twitter is. So you're wondering, what's the probability that I'm going to go ask 5 people what Twitter is, and 3 of them, exactly 3 of them, will say yes. Okay? So then we have to ask ourselves, does the procedure result in a binomial distribution? In order to do that, you have to argue the 4 things we just satisfied. The number of trials is 5. Okay, that's fixed. We're asking 5 people. Okay, we fixed that. The 5 trials are independent. If I ask someone at the grocery store if they know what Twitter is, and then later I'm at the pharmacy and I ask someone else what Twitter is, there's no connection between those 2 people. They are independent events. Okay. Each of the 5 trials has 2 categories of outcomes. Yeah, you either know what Twitter is or you don't. There's only 2 outcomes, right? That's why. So remember, you all hopefully asked a 2-outcome question. If you didn't, just steal another one from the survey. For each randomly selected adult, there is an 85% probability that the person knows what Twitter is, and the probability remains the same for each of the 5 people. So it's not like, if I ask someone in the VC parking lot if they know what Twitter is, and then I ask someone at Vaughn's, that probability is staying the same. It's not changing depending on where I go. Okay. In this procedure, if the procedure does result in a binomial distribution, which we just argued that it does, identify the values of n, x, p, and q. Okay, so n is the number of, let's see, where are we? N is the number of trials we're doing. We already said we're asking 5 people, so our n is 5. Okay, now we want to know about having 3 successes, so our x is 3. We're told in the problem that the probability of someone knowing what Twitter is 0.85. So P is easy, that's 0.85. So what would Q be? That we weren't directly given that information in the problem, but remember Q, the probability of a failure, is 1 minus the probability of a success. So 1 minus 0.85 is 0.15. So there's your Q. Okay? So then you stick them into this formula right here. You've got your N. See, everything up here is an N, an X, a P, or a Q. So you can just stick them all into your formula. You can do it in Wolfram Alpha if you want, right? You could be careful with your syntax, but when you put it in there, it goes into Wolfram Alpha and figures it out. You can do it with Statcrunch. Numerous different ways of getting that down. Just Google or just go into YouTube and type Statcrunch binomial probability formula, and there'll be someone showing you exactly how to do that on there. Okay, do remember that 0 factorial is 1, and that in general the factorial is that number times all the numbers down to 1. Okay, so it looks like this. If you take the numbers that we just did from that problem and stick them in here, remember our n is 5, our x is 3, and then we've got our p and our q. So you just plug them all in and then let some calculator, Wolfram Alpha, whatever, do it for you, and you get 0.138 rounded. So the probability of going out, asking 5 random adults if they know what Twitter is, and getting exactly 3 who say yes is 0.138, right? So there's really, 5 outcomes. You can have, well, it gets a little trickier than that, but you can have 1 person know what Twitter is. I guess you could have 0 people know what Twitter is, 1 person that knows what Twitter is, 2 people that know what Twitter is, 3 people that know what Twitter is, 4 people that know what Twitter is, or 5 people that know what Twitter is. So I guess 6 outcomes there. Some of these questions will ask you specifically, like this one. What is the probability that exactly 3 people know what Twitter is? And this is what you'd do. What if the problem said, what is the probability that more than 3 people know what Twitter is? Well, then you would have to calculate this for 3 people knowing what Twitter is, then calculate 4 people knowing what Twitter is, then calculate 5 people knowing what Twitter is, and you would add those probabilities together. So see how our chapter on how probabilities work and when to add and when to subtract and stuff like that come together? We're starting to use it right now. So when you see problems that say 3 or more, like if it says exactly 3, you do it just like we did here. If it says 3 or more, Then you calculate 3, 4, 5, you know, the probability of 3, the probability of 4, the probability of 5, and you add those probabilities together. Okay. So just watch the language carefully, because you might be looking, you know, you might look at the video where we worked through this one and say, well, isn't this one in the homework that says 3 or more? Isn't that the same as this one that we just did? No, this one was exactly 3. You'll have problems where they do 3 or more. So just be careful with that. Let's see, where are we on time? I got a little bit of time to talk still. Where was the next thing I wanted to do? There was one in here. There was something else in here I wanted to look at. Was that everything? I thought there was something else I wanted to go over. Nope, looks like that's the end of the chapter. Okay, so we've got about 7 minutes left. Okay, so let's do the thing I skipped earlier, where we were going to go in and we could actually make a game. So we've got what? We've got our, just to remind you how expected value works. So we've got our outcomes, we've got our payoff, and then we've got our probabilities. How you spell probabilities? I don't know. Anyways, so let's just say we're going to make a dice game. We're going to keep this real simple. We're going to roll a dice. I'm creating a game. We're going to play it. And under certain circumstances, I pay you certain amounts of money. Under other circumstances, you pay me certain amounts of money. So we're making up a game, and we'd like to know, well, what do you expect to happen in the long run? Right? So let's say we're going to roll a dice, so there's 6 outcomes. 1, 2, 3, 4, 5, 6. Okay? So now you decide the payoff. Okay, so we'll say that this is from the, well, let's make it from my perspective, since I'm making the game. I'm the creator, right? I'm the casino. I'm making a game, and I want to make sure that in the long run, the money is moving in my direction, not that the casino is paying out money. We want the money coming in. Sure, any individual might make some money in the short term, but when millions and millions of hands are played, the average, the mean, is that the money's coming to us, right? So the payoff, let's say that if a 1 is rolled, I pay you $2. If a 2 is rolled, I make $3. You pay me $3. If a 3 is rolled, then I pay you $4. If a 4 is rolled, you pay me $1. If a 5 is rolled, you pay me $1. And if a 6 is rolled, I pay you $3. Okay? Well, so what do we expect to happen in this game? If you just sort of look at it, it's kind of hard to figure out what the overall, you know, in any given hand, we know what can happen. You just look at the number and then, oh, that's the payoff, right? So, but what happens if I play this game 1,000 times? What's going to happen? Do I expect to make money or lose money? I don't even know, because I just made this up. So let's see. The probability of each of these is 1/6, right? Actually, let's do this. Let's do this way. It's going to be 0.16667.1. I'm just rounding here. That's the decimal rounding of 1/6, right? So our expected value then is where we're going to estimate the outcomes. Like you could say, well, aren't our outcomes the dice? Right, but at the end of the day, like, what's the real consequence of your action? It's the money that you have to pay. Either I'm paying you or you're paying me. So we would go through and we're going to calculate each of these values. So if I do times -2. So if I multiply across here, I get, oops, my negative didn't count for some reason. This is going to be -0.3333333333. This one, when we multiply across, so we get 1/6 times 3, we get 0.5. Oh, that makes sense. 3 times a 6 is 0.5, right? 0.5, right? Down here, we're just going to get 0.16667, 0.16667. Down here, we're going to get negative 0.5. And up here, we're going to get, let's see, what's 1/6 times 4 is going to be, so this is negative 0.6666, oops, negative 0.66667. And we're going to have some rounding errors probably because I rounded things off a little bit. But this is our XP category, right? This I'll write it. This is our X times P of X, right? That's that category where we do the X times P of X. And then down here, we want to add all these up. So just, I'm just going to go through and add them all up by hand. So let's see what we get. We get 0.3333333 negative. So we can actually simplify things here a little bit. Look, this 0.5 here and this negative 0.5 down here, those just cancel each other out. So we don't even have to do that as part of the calculation. And then we've got minus 0.66667 plus 0.16667 plus 0.16667 equals, and it looks like we get if I did all that right, it looks like we get 0.66666, bunch of stuff, as our expected value. So basically when we round it, it comes to this, which would mean every time, on average, every time that you play this game with me, I'm going to get 2/3 of a dollar from you. I'm going to get about 67 cents. I'm going to win each time. So you might, in any given roll, win. You might roll a 2 and win $3 right out of the gate. But if we play this 1,000 times, then it's going to average out pretty close to you losing 67 cents every time we play. So that's just like we looked at the roulette and craps games earlier, where every time you play, you're going to lose 7 cents. You're going to lose a quarter. You're going to lose whatever. This is high. People would probably get. There's this whole psychology they use in casinos, which is if you're losing 2/3 of a dollar every time you play, you're going to be losing a lot. If that's your average, you're going to leave the casino. That's not very fun, because the whole thing is when you win, you get excited, and that excitement carries you through the losses till you get another win again, and then you're like, I can get it back, and you start playing this whole psychology game. That's why the numbers we saw for an actual game were lower than this, right? 7 cents. They want you in there for hours because you could argue they're providing you entertainment, right? If you're losing 2/3 of a dollar every time you play, your money's going to go pretty quick. So you would want to adjust this. You'd play around with these numbers till you got something that's more like, and we could actually automate this if we had a little more time. We could automate this in Statcrunch so that when I change these values, it changes it does the calculations for us automatically, right? There's if you go into data, it's just like in Excel where you can have it calculate stuff for you. Where is it? I'm trying to remember. Compute. Yeah, you can put in expressions just like you can in Excel and have it compute stuff. So you could create a game like this, and you could try to make it real even so that maybe on average a person only loses like the craps game, 7 cents each time. If they're losing on average 7 cents, that means a lot of times they're gaining money, a lot of times they're losing money, and then over time it ends up just being a loss of 7 cents each time. That's going to be much more exciting for a person to play. That's how casinos work. Everything they have has an edge, but just barely, right? If the edge is too much, people stop playing that game because they're like, I'm just pumping money into this game. I'm not getting anything out of it. Okay, so with that said, as always, feel free to jump into Zoom after class and talk to me about whatever you need. In the meantime, make sure you're finishing up and preparing to have Chapter 6 due. Make sure you're doing this part right here so that you get that taken care of and get those kind of easy points. I'm not saying don't do a good job. Try to do a legitimate job. That's the way you get 10 points is I look at it and go, did this person honestly try to do the assignment? But I'm a little easier with my grading now than I will be in another 7 weeks when we're finishing things up. I will expect you to understand it a little better by then. But for now, come in here, make an honest effort, get your 10 points. It's going to help with your project grade overall. Okay, so that's where we're at. Feel free to hop into Zoom. Otherwise, I'll see you next